Okay, good afternoon, everyone. I've got just a couple more seconds until 3:20, so let's begin. Um, so let's start with looking at the web page and take stock of where we are. There is a quiz today, and let me just remind you, here's the page on instructions for taking quizzes. Please note that quiz 2 is today, Tuesday, January 26th. So the availability is 6 p.m. to 2 a.m. So that's Tuesday today, 6 p.m. to Wednesday, 2 a.m. All these times are Pacific time, of course. It's pretty much like the last quiz. It's going to be 2 questions. They both pertain to BFS. That's as much as I'll say right now about the quiz. So good luck on that quiz. I think everybody should be in good shape. I mean, we're not behind or anything. So we've covered that material some time ago. So you should be fine. If you should have any technical problems during the quiz, you know who to contact, TA Schwan and Lin. And I understand there's supposed to be a really bad rainstorm in Santa Cruz County. So nothing I can do about that, obviously, but if you should lose your power or something like that, then just do the best you can. If you can't do anything, then we'll talk about it afterwards, right? That's the best I can tell you. I wouldn't want to specify what would be done until I find out for each student what exactly happened. That's what I'm trying to say. So I'm not going to make some kind of general policy about it, but just do whatever you can. Okay, so I'm going to close that. Nothing else to say about the quiz. Well, I'll write this down. Quiz 2 today. And then what else? Well, PA2 was extended one last day, Sunday, January 24. So that was the last one. It's now closed. Hope everybody got something turned in. PA3, as of this moment, is due this Friday, January 29 at 10 p.m. Please, everybody, remember that there's always a built-in 12-hour grace period. 12 hours means that when something is due at 10 p.m., as it always is, it's actually due, kind of a fiction, it's actually due 10 a.m. the next morning. That's the real deadline. So PA3 is set to close on Friday. I think I've got to cover some more stuff today before you really know how to build that top-level client. Of course, it's doable without today's lecture because everything you need to know is in the textbook. But you will have noticed that my handout on graph algorithms stops kind of abruptly at the notion of topological sort. And I didn't really get around to saying what a topological sort is. And there's nothing here about strongly connected components. Well, I'm going to cover all that today. Like I said, it's all in the book, and what you're experiencing with this abrupt halt here is the fact that this handout is not complete. I've only got 9.5 pages. I probably need 5 more pages. Okay, so I'm just going to pick up where I left off last time, except, oh yeah, somebody no doubt wants to ask me for an extension. Is that the case? Let me just say yes if you're asking for an extension. Wow, I've only got only 2 people. You got to hit the yes button. Yeah, because that's the only way I can count. Yeah, a lot of people are chatting it. The yes button is what I'm looking at. Okay, so I tell you what, I will push back a day, and then come Thursday, when we meet again, I'll consider another one. Okay. So going back to this, so PA3 extended one day. So instead of Friday, it's Saturday, 10 p.m. By the time we get through today's lecture, I think it really will be possible for the majority of people to be done by then. Okay. So where were we last time? Well, we were talking about depth first search. And I would like to, well, no, I won't quite do this yet. At a certain point in the discussion, I'm just going to restrict all discussion to directed graphs, because PA3 is really about directed graphs. But for the moment, a lot of things I say, a few things that I say will also pertain to undirected graphs. The last thing we talked about was the notion of classification of edges. When you run DFS and look at the predecessor subgraph, any edge that belongs to that predecessor subgraph is classified as a tree edge because it belongs to a tree in this DFS forest. A back edge is any edge that joins a vertex to an ancestor, one of its ancestors. A forward edge is an edge that joins an edge to one of its descendants, other than a direct child. After all, if the edge that goes from a vertex to its child is already classified as a tree edge, so it's not also classified as a forward edge. If you go further than that, an edge that goes down further than one generation, that's called a forward edge. Cross edges are everything else. Now, I did one example. Let me do another example just to freshen this up in our mind of this edge classification, because it is useful. So here is a graph. Everybody can see this, I hope. The digraph. So here are the directed edges. It's like 7 vertices. I'm going to run DFS on this. And I'm going to do the visual approach. You should do it both ways, right? You should fill out the table with the adjacency list representation, color, discover, finish, and parent. But you can also do that, you know, kind of in a standalone fashion by running DFS. So what do? Main loop of DFS, you discover 1 and visit it. So let's draw the DFS forest. As we go. So 1, since it was discovered in the main loop of DFS, or by calling visit in the main loop of DFS. And just to remind you of what I mean, there's DFS, and this is what I mean by the main loop of DFS. Our convention states that this loop will be executed in increasing vertex label order. At a certain point in a certain algorithm that has to do with PA3, that convention will be altered. This loop, we also have the convention that this adjacency list is processed. This loop is executed in increasing vertex label order. That convention never changes. Okay, we need a convention, otherwise we don't know what to do next in the for loop, in these two for loops. All right, so going back, what do I discover after what do I discover next? So from 1, I can discover 2 or 4. Always choose the lowest label. Put all the things that you can discover now and discover the one with the lowest label first. From 2, I guess I'll draw this when I start returning. From 2, I can discover 3 or 4, so choose the lower label. The reason you choose the lower label is because of our convention on the for loop in visit, right? Those vertices are processed in increasing vertex label order. From 3, I can discover nothing, so I finish 3 and return to 2. From 2, I can discover 4, so I discover 4. And from 4, because out degree 0, I can discover nothing. So I finish 4, return to 2. From 2, I can discover nothing new, so I finish 2. Return to 1. From 1, I can discover nothing, so I return to 1. Now I didn't keep up here. From 1, I discovered 2. From 2, I discovered 3. Then I returned to 2, and then from 2, I discovered 4. Return to 2, return to 1. That was this little part. So I discovered these 4 vertices. Now I'm back at, and I'm returning from a call to visit 1. I'm back in the main loop of DFS. By this time, 2, 3, and 4 have already been discovered. So in that main loop, I come to 5. Now we discover 5. From 5, I can discover 6. From 6, I can discover nothing new, so I finish 6, return to 5, and from 5, I can discover nothing new, so I finish 5. Now I'm back in the main loop of DFS again. So the next one is 6, but that's already been discovered. The next thing is 7. So 7 is discovered. From 7, I can discover nothing new, so I finish 7. And I return from the call to visit 7. So I'm back in the main loop of DFS, and I'm also at the end of that main loop. So here it is. Here's the DFS forest. And if I wanted to fill in the table, I could extract from this tree the discover and finish times. Discover, 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 finish, return, discover, finish, return, finish, return, finish. Discover, discover, finish, return, finish, return, discover, finish, return. Okay. So I could get all those discover and finish times and fill in a table if I really wanted to. Everything is always black at the end of DFS. There is no source. Let me say it again. Some people get confused. What was the source on DFS? There is no source in DFS. There's a source in BFS, not DFS. What about, yeah, what else?
Well, whatever else you have to fill in. The parents, right? This DFS forest tells you who is the parent of who and who's the child of who. Now let's take this predecessor subgraph and shade those edges in the original tree. I mean, in the original digraph. So 1, 2, 3, 4, 4 edges, and those are them. So we're going to classify the tree edges okay, edge classification, it didn't quite fit. So the tree edges are those that belong to the DFS forest. 1, 2, 2, 3, what else? 2, 4, and 5, 6. Okay, edges that go from a vertex to an ancestor. Well, there's this edge from 3 to 1. Let me put it in here. I'm going to redraw the graph here. So all tree edges go down in this drawing. This is goes from 3 up to 1. So there is what we mean by a back edge. And I believe there's only one back edge. 3 to 1. And there's another one, 1 to 4. That's what we mean by a forward edge. Yeah, I just noticed something, and that is when I'm looking at my notes, you may have noticed this too. Is anyone noticing this? In my notes, I had this direction different. So I had another tree edge, namely 5 to 7. But I'm going to stick with the way I'm running it, stick with the example. This departs from example 6 on page 9 of the graph theory, or rather graph algorithms handout, just because I copied the direction wrong. And rather than change it now, I'm just going to go directly with the example as we've done it. 3 roots. This tree has only one vertex in it. That's fine. So there are only 4 tree edges, therefore. What else? And there, let's see, there's one forward edge, that's 1 to 4. And what about cross edges? Cross edges, okay. Well, 5 to 2 and 6 to 4 are tree to tree. And 7 to 5 and 7 to 6 are also tree to tree. And it doesn't look like that there are any cousin to cousin. Whereas if I had reversed this edge, this would end up being a cousin to cousin. Anyway, they're all cross edges. So 5 to 2, 6 to 4, 7 to 5, and 7 to 6. Okay, that's the edge classification. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every edge has been classified. Okay, that's good. Now, what is this edge classification good for? I'll tell you that in a minute, but let's just point out that the edge classification does depend on the order in which we process.
There's some hands that are raised.
Lots of hands are raised. So let me look at a couple of hands are raised. Okay. Hansel, go ahead and unmute yourself. How can I help you?
I have a question about why, like, I get why 1 to 4 and 3 to 1 are like forward and backward edges, but what about, could you explain like why, like, let's say 2 and 4 and 2 and 3 aren't?
Well, there is no edge from 2 to 4.
Okay.
2 to 4. I'm sorry, 2 to 4. Yeah, these are tree edges. They belong to the tree.
Okay. Okay. I see.
Yeah, and the way the book explains it is this: you go down this list of categories in order, and you assign an edge to the first category that it can fit in. So these edges have been assigned to the tree category. So even though they do go to a descendant, we don't assign them to the forward category.
I see.
That's the rule as the book explains it. The way I explain it is just saying tree edges are parent to child. Forward edges are ancestor to descendant other than direct child.
Okay.
So this is a child. 4 is a child of 2. 3 is a child of 2. So that's why these are considered tree edges, but not forward edges. They can't be both, right? These are disjoint categories.
I see. So it can't be like one like edge cannot be classified as more than one.
That's correct. That's correct.
Okay.
The edge classification is each edge has a unique classification.
Okay. All right. Thank you.
So the edge classification does give us some structural information, as I'll get to in a minute. But second question, Cal Ruiz. Go ahead.
Hi, I just wanted to ask, will these qualities for edges, such as back, forward, cross edges, are they going to be of importance for PA3, or will they mostly be related to like quiz questions?
Well, you don't have to do the edge classification in PA3, although it's sort of necessary for understanding what's coming.
Okay.
So no, you don't have to do this. You don't have to do the edge classification, although I could ask you this on the next quiz, right? Quiz 3.
Okay.
Okay. So you are seeing this, right? Okay. So here is an exercise. Run DFS on all previous examples, you know, like the DFS examples, and classify edges. And then alter the labels. And run DFS again. Classifying edges. You see that the edge classification does end up depending on the labeling, as long as you stick to our convention. Equivalently, you could just change your convention, you know, do something in a different order. And an edge that might have been called a forward or back or a tree will be something else second time around if you do things in a different order. It's a little hard to believe at first that the edge classification tells you anything intrinsic about the digraph itself. I just want to illustrate, I just want you to illustrate that to yourself. It is dependent on the order in which we execute these loops. Let me say something else about the edge classification. When I give you these 4 categories, those are the 4 categories you get for directed graphs. However, in the case, I don't know if anybody's noticed this, nobody asked about it. For an undirected graph, there's no way to distinguish between back and forward, right? Because how do you know if an edge connects an ancestor to a descendant or that descendant to an ancestor? It's a two-way street in the case of an undirected graph. So there's no way to distinguish between these two. So the way I put it is these 4 categories are for digraphs. If it's an undirected graph, there are only 3 categories: tree, back, and cross. So just logically, you leave out forward. Everything in forward becomes a back edge. The way the book's rule also takes care of this, right? Go through these categories and assign each edge to a category, to the first category that you can. Well, if you can assign it to back, then you can't assign it to forward. So everything, even in an undirected graph, everything, all back and forward coalesce into a single category. Anything that could have been classified as forward was already classified as back. So the forward category disappears logically for undirected graphs. What else? So in spite of the fact that it looks like this is meaningless or doesn't help, do this. Modify DFS. So that it prints each edge along with its classification.
Pat, you have questions
So,
again?
Chris, go ahead and unmute.
I had a question in the previous example. Are 3 and 4, do they have any like relationship with one another?
3 and 4?
Yeah, specifically in the forest diagram.
Well, there's no edge joining 3 to 4 or 4 to 3. If that's what you mean.
So they wouldn't be cousins or siblings.
Oh no, no. Well, they're siblings.
Okay.
Yeah, they are siblings because they're both children of 2. But there's no cousin to cousin edge. There's no cross edge that connects cousin to cousin, if that's what you mean.
Okay, yeah, I was just clarifying because there was some confusion.
Yeah, I would refer to these as siblings. Yeah.
Okay, gotcha. Thank you.
Okay. Okay, so print out each edge along with its classification as you go. Let me just give you a little, oh, first of all, hint, page 609 through 610 in CLRS, 22.3-10, problem in CLRS. So, so there's my hint. The book says something about it. And let's just look at DFS for a second and look at visit. Well, as soon as you color, as soon as you see that a vertex on X's adjacency list is white, so if you're inside the true branch of this conditional, the very first thing you do is set parent of Y to be X. That establishes
X to Y as being a tree edge. So at this point, you should print X comma Y is a tree edge. And the key is, the key to doing this exercise is to add some else if, else, or something like that. Add some other conditionals, a cascade of if, else if, however long is necessary after this if. So if this is white, fine. But what if it's black? What if it's gray at this moment in time? That's how you're going to print out the classification of each edge. So, and that's what the hint in CLRS is about. So I'm just going to leave that. Basically, it's to play around with this conditional and add some else's to it. All right, that's another exercise, a very good exercise.
Pat, there's a question on example 1.
Okay, Adam, go ahead.
So by altering labels, do you mean just changing the order in which DFS is processed?
Yeah.
Okay.
Yeah, remember we have a convention, so you can do two things that are equivalent. You can not run the for loop in increasing vertex label order.
Mm-hmm.
So vertices are processed in a different order. Or you can stick to the convention and change the labels. That also causes, vertices to be run in a different order in the adjacency lists and in main loop of DFS. All those orders are going to affect who gets to be tree, who gets to be back, who gets to be forward, and who gets to be cross.
I see. But if you change the labels, wouldn't it be hard to tell which edges are edges?
Only if you keep track of what the label used to be.
Okay.
Right, you keep track of what the vertex, what labels used to be, and then so maybe that's 1 and that's 3. So this edge is going to be 3 to 1 in the new labeling, and that's going to be compared to 5 to 2 in this labeling.
Okay.
See what I'm saying?
Yeah, I see. Thank you.
Okay, so you compare actual physical edges to physical edges,
Mm-hmm.
right? With their new names, with their new labels.
Okay.
And with that understood, who gets to be who? Now each edge now has a different name because it has different end vertex labels, but they also get to be, they show up in different points in this classification.
Interesting.
Okay. Well, I like these clarification questions to make sure that everybody understands exactly what the exercises are suggesting. Here's a theorem. The theorem says if DFS is run on an undirected graph, then there are no cross edges. So going back to the edge classification, let me bring this up. There's the edge classification. So as I pointed out, for undirected graphs, back edges and forward edges coalesce into a single category called back edges. And cross edges are eliminated by this theorem. So in an undirected graph, there's only 2 categories, free edges and back edges. And in that case, this also is, it's the main fact, this theorem, this result is the main thing that proves the theorem that says in an undirected graph, each tree spans a connected component.
So it's the basis for another exercise I gave that said, rewrite BFS and add a CC component to each vertex, or a CC stamp, connected component stamp. And that would be for undirected graphs only. All right, I'm not going to revisit that, that fact. Okay, one more exercise. Oh yeah, that was the exercise. I see the exercise I have here, exercise 5 on page 10, is the exercise I already gave some time ago. All right, so now let's talk about the next section in the textbook, and that is topological sort. This does pertain to the edge classification, and it does also pertain to PA3. So from now on, let G be a digraph. Okay, so I'm not talking about undirected graphs anymore. Everything's a digraph. We say G is acyclic if and only if G contains no cycles. No directed cycles. Otherwise, we don't call it cyclic. We don't call the graph cyclic. We just say it's not acyclic. So here are what cycles look like. Directed cycles. Well, the trivial path is never considered a cycle. But in a directed graph, it's okay to have a self loop. By the way, you can't have self loops in undirected graphs because that wouldn't be an unordered pair. That would be a one element subset, not a two element subset of the vertex set. But remember, in directed graphs, these are ordered pairs. So x comma x is a valid ordered pair. So length, the length is 1 in this case. Here is something else that you can't have in an undirected graph, parallel edges, as long as they go in different directions. X comma y and y comma x. This is length 2. Then a 3 cycle. Length 3, and then 4. Okay, so these are directed cycles. And there's a directed cycle for every possible length. If one of these digraphs is a subgraph of G, then we would say that G is not acyclic. Otherwise, it is acyclic. Now, an example, a couple of examples of digraphs. Okay, so take a look at that, and you'll notice there are no directed cycles in it. So this is acyclic. Here's another digraph. all I'm going to do is change the directionality of one edge, and we'll see that it does have a directed cycle. So I've changed the direction of 1 to 3. 1 to 3 is flips to 3 to 1. Okay, so this does have a directed cycle, and so this is not acyclic. Okay. Well, what is it about directed cycles and the edge classification? Lemma. A digraph G is acyclic if and only if DFS run on G yields no back edges. Notice when I said DFSG, I didn't specify the order in which the loops are going to be executed. I didn't specify a convention for this. And it doesn't matter what the convention, it doesn't matter what the order is. You know, it might not be obvious when you look at a gigantic digraph whether it's acyclic or not. If you can't tell, run DFS on it and classify edges as you go. And if you find a back edge, there is a directed cycle. If there is no back edge, then there is no directed cycle. So equivalently, if and only if statement. So I can negate this statement and negate this statement, and I get another way of saying the same thing. G contains a back edge. If and only if G contains a directed cycle. Okay, so in spite of the fact that the edge classification seems to depend on our convention, regardless of the convention, DFS can be used to detect this structural feature in a graph, in a digraph. That is the existence or non-existence of a directed cycle. Now, what do we care about directed cycles? Well, here's a definition. Let G be a digraph. G is called a directed acyclic graph. Directed acyclic graph, if it is a directed acyclic graph. If, or also called a DAG. If it is acyclic. Kind of obvious, right? Directed graph with no cycles that is acyclic. It's called a directed acyclic graph. All right, so what's important about DAGs? A common use of directed graphs is in scheduling problems. Suppose you have some kind of job that can be broken up into 4 tasks, 1, 2, 3, 4. And you don't know in what order you are going to schedule the 4 tasks, the 4 subtasks, if you like. But all you know is this: 1 must be performed before 2. 2 must be performed before 4. 3 must be performed before 4. 1 must be performed before 3, and 2 must be performed before 3. Can you write a schedule? No, you can't, because the must be performed before then relation has a cycle. Yes, you can in this case. Yes, you can in this case, because it's acyclic. But you can't do it in this case, because in this case, the must be performed before then relation has a cycle of dependencies in it. You got to do 1 before 2, 2 before 3, and 3 before 1. Well, there's no way to do that. Let's put it this way. You'd have to figure out some way to do all these tasks simultaneously, or break your problem into subtasks in a different way. If that really was a constraint, you got to get around that constraint somehow. So when it comes to scheduling problems, you do care about cyclic dependencies. And this is a common way to use a digraph to represent scheduling constraints. The must be performed before then relation is like the edges, the edge set, basically. Okay, so you do care if a graph is a DAG or not. If it's a DAG, you can write the schedule. If it's not a DAG, then you can't write the schedule. How can you tell? And what would your schedule be? What do you do first, second, third, fourth? So here's another definition. A topological sort of a DAG G is a linear ordering of the vertex set of G such that if the ordered pair X, Y is in the edge set of G, then X is before Y in the linear ordering. To put this another way, if you take all the vertices in the graph and you draw them along a horizontal line, so they're on a horizontal line, and then you draw in all the edges go from left to right. Sorry, you draw them along a horizontal line in this linear ordering. Then if you draw on the edges, all the edges go left to right. So look at this example. And we just looked at this. Here is an acyclic graph. 1, 2, 3, 4. Don't ask me why I'm relabeling the vertices. I don't want to fight my my notes, so I'm going to stick with what I have in my notes. Okay, so remember, this is acyclic. This is a DAG. By the way, only a DAG can have a topological sort. If it has a directed cycle, then you can't have, no matter how you draw it on a horizontal line, you can't have all the edges going the same direction. If it has a directed cycle, one of the edges has to go back. So here is a topological sort. of G, call this G. Take the vertices and arrange them in this order. This is the linear order. 1, 4, 2, 3. So that's a topological sort. How can we tell that it's a topological sort? Draw in all these edges. 1 to 4. 1 to 2. 4 to 2. 2 to 3. And 4 to 3. There. For every edge, the origin comes before the terminus in this linear order. This is what we mean by a topological sort. Now this tells us, if you look at this and you suppose 1, 2, 3, 4 are subtasks in a scheduling problem, and this DAG tells you the must be performed before then relation, then 1, 4, 2, 3 is a viable schedule. On the first day, do this task. Second day, do this task. Third day, do this task. Fourth day, do this task. So that's what topological sorts are. One good thing, therefore, is scheduling problems. All right, so what does this have to do with DFS? DFS can give you a topological sort of a DAG as follows. This is page 613 in the LRS. And I believe the algorithm is called topological sort in that in the book, but I'm not going to call it that here. So to perform a topological sort, on a DAG, G, do this. So here's some pseudocode. Run DFSG. Now, as vertices finish, that is, at every finish event, that's where you blacken a vertex. Take that vertex and push it onto a stack. So as vertices finish, push them onto a stack. When you're done, when DFS is run and you've pushed every vertex onto the stack because everyone finished and everyone is black, the stack is your topological sort. And by that I mean top to bottom. Right, so that's the linear ordering. Go from top to bottom, make that horizontal. Think of your stack as horizontal, top on the left, bottom on the right. That's your topological sort. So I'll tell you what, let's do this in an example. By the way, notice I always say a topological sort. There might be other topological sorts. There might be more than one. In this particular case, there is only one topological sort, and the reason is because of this Z, 1 to 4 to 2 to 3. That has to go left to right, and that includes all vertices. So that's the only topological sort there is. But in the next example, we'll see that we're going to get a topological sort, but there's more than one. So here's an example. 1, 2, 3, 4, 5, 6. Again, I don't know why the labels are chosen in this particular way. Okay. So let's run DFS and I tell you what, I'm not even going to draw the forest, but I am going to keep track of the stack when I finish. So, so using our conventions, start at 1. From 1, I discover the lowest possible label, which is 2. From 2, I can discover nothing else. So I finish 2, push that onto the stack. Return to 1. From 1, I discover 4 or 3. I pick 3 because it's a lower label. Again, that's just our convention. From 3, I discover 4 or 5. We pick 4. From 4, I discover 5 or 6. We pick 5. From 5, we can discover nothing else. So we finish 5, push 5 onto the stack, return to 4. From 4, we can discover 6 and then nothing else. So we finish 6 and push it onto the stack, return to 4. Finish 4 because you can discover nothing new from 4, push 4 onto the stack. From 4, you return to 3. I just want to make sure. Yeah, I return to 3 and can discover nothing new from 3. So we finish 3 and push it onto the stack. From 3, return to 1. Yeah. And from 1, I can discover nothing new. So I finish 1 and push 1 onto the stack. 1, 2, 3, 4, 5, 6. All vertices have been finished and all vertices have been pushed onto the stack. So the theorem says that our topological sort is 1, 3, 4, 6, 5, 2. Let's fill in the edges. I got 1 to 3. I've got 3 to 4. I've got 4 to 6. I've got 6 to 5. And I've got 1 to 2. And I've got 3 to 2. 1 to 2 and 3 to 2. Nothing from 2 to anything. And I've also got, what, 3 to 5. What else am I leaving out? 1 to 4 and 4 to 5. So I've got 1 to 4 and 4 to 5. Okay, let's count edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I've got all the directed edges. And indeed, when I draw it this way, all edges go left to right. That shows that this linear ordering given by this stack. So the stack is decreasing finish times. and it gives us a topological sort. So now let's think about scheduling problems. You have some big complicated digraph of must be performed before relations, subtasks, and the must be performed before relation on those subtasks, on pairs of subtasks. So you don't know if there's a cycle in it or not. So you could run DFS, classify edges as you go, check and see if there's a back edge. If there's a back edge, forget it, you can't schedule. But if there's no back edge, then it's a DAG, so it does have a topological sort. So you run DFS again, pushing vertices onto the stack as you go, and that that stack gives you your topological sort, and there's your scheduling. Did I really need to run DFS twice? No, you don't. You could do both at the same time. Run DFS, classify edges as you go, and push onto the stack as you finish. Now look at your edge classification. If there's a back edge, then look no further. But if there's no back edge, look at your stack. That's your topological sort. So that's the most efficient way to schedule. And you can also find out if there is no scheduling. Your constraints tell you that no scheduling is possible. All with one call to DFS. Now, I said there was going to be more than one topological sort. Just looking at this topological sort, you can imagine these directed edges are made out of rubber bands or something. So I could put the 2 anywhere other than before the 3 or before the 1. See, if I picked up this 2 and tried to put it before the 3, then the 3-2 edge would go backwards. Can't have that. Likewise, if I tried to put it before the 1, then the 1-2 edge would go backwards. But as long as I put it either here between 3 and 4, or here between 4 and 6, or here between 6 and 5, or where it is, then I should have a valid topological sort. Actually, I solved the next exercise. I inadvertently did it. So, exercise. The last example has 3 other topological sorts. Find them. How come DFS didn't find, how come DFS, so altogether there are 4 topological sorts, this one and the 3 others that I already told you what they are. So what would it take for DFS to find something different? Find one of the other ones? This is where our conventions come in, and this is where the ordering of the vertex labels come in. Change the labels, rerun the whole thing, keeping track of the old labels so you know you have a dictionary that takes you between them. And you might get a different topological sort. Do that also. Exercise. Try to, so change labels around. Permute labels. And find the other topological sorts. Using the algorithm. Which algorithm? This algorithm. So this, I believe this is called top sort in the textbook. And I didn't write it as pseudocode, I just wrote it as pseudocode, a bulleted list of things to do. All right, so that's something that could happen on a quiz, not the quiz for tonight, but maybe on quiz 3. And now we get to the subject of PA3. That is strongly connected components. SCC. SCCs are the strongly connected components. So let me remind you what the strongly connected components in a digraph is. Let BE be a digraph. A subset U in V is called strongly connected if and only if every vertex X in U is reachable from every other vertex Y in U. And conversely, don't really have to say conversely because I said every vertex. So for every pair of vertices in X, X, Y, and U, there's a directed path from X to Y and a directed path from Y to X. They're not necessarily the same directed path. In fact, they can't be, right? Because these are one-way streets we're talking about. So a strongly connected, a subset of the vertex that is strongly connected, that just means you can get from anywhere to anywhere in that set. Further, U subset of V is called a strongly connected component SCC if and only if two things. One, U is strongly connected, and two, U is maximal with respect to 1. WRT means with respect to. So in other words, whenever U is a subset of some other set W, but not equal to it, which is also a subset of the vertex set, then W is not strongly connected. In other words, you can't grow and retain strong connectivity. That's what we mean by a strongly connected component. Okay, so we should maybe look at an example, some strongly connected components. And by the way, this is not necessarily a DAG. Let's look at this example. One of our examples earlier. I won't label the vertices like I did before. Just draw on the edges and show you the strong components. Okay, so the first thing you notice is that I can get from here to here to here to here. So this subset of the vertex set has the property that it's strongly connected. I can get from anywhere to anywhere. On the other hand, if I were to throw this vertex in, I lose the property of being able to get from anywhere to anywhere. Because if I included this vertex, I could get, I made a mistake, sorry. Sorry about that. And this is the digraph I had up before. I started talking about acyclicity. So if I were to add this vertex to this set, then I'd have a set, namely the whole vertex set, where I could get to this point, but I couldn't get out of it. I can get from here to here, but I cannot get from here to here. Or I cannot get from here anywhere because there's nothing but incoming edges. So this is a strongly connected component. Call it SCC1, because it's the first strongly connected component. What about this vertex? Does it belong to a strongly connected component? Sure, it does. Every vertex belongs to a strongly connected component, namely the singleton set containing nothing but itself. So that is another strongly connected component. Call it SCC2. Is that clear? So these groups or these subsets of the vertex set form the strongly connected components in this digraph. Think of this directed cycle as kind of like a bus line. You can get off anywhere, get on anywhere. So you can get from anywhere to anywhere. But this single vertex is only one. You can get from this vertex to this vertex by the trivial directed path. But by no other means can you get from here to anywhere else. There's no other place you can get to except from here to here. So this singleton set is a strongly connected component. Okay, so that illustrates what I mean by strongly connected components. This is page 8. And now we have a problem. And the problem is, how do you find strongly connected components in a digraph? Answer, use DFS. So remember, I promised you that DFS was going to be shown to be useful, good for something. Here it is. Find the strongly connected components in a diagram. Follow the following pseudocode. Call or run DFS G. As vertices finish, push them onto a stack. Then what? Compute the transpose. GT of G. Transpose of the directed graph. What's the transpose? I didn't define that yet. The answer is just reverse all the directions. So go throughout the graph, maybe in the middle of the night as an act of vandalism, and take all the one-way street signs and turn them around. I don't know why I thought of that, but just do it. In other words, the directed edge XY is in the edge set of G if and only if the directed edge YX is in the edge set of G transpose. So that's the relationship. Just swap all directed edges. Now run DFS on G transpose. But now we change the convention on the main loop of DFS. Now, process the vertices in the main loop by popping vertices off the stack. So equivalently, you go through those vertices, you go through the vertices in the main loop of DFS by decreasing finish times from the first call. Main loop is run by, instead of increasing vertex label, our convention, decreasing finish times from first run. Of DFS. Okay. So you're done now. How am I done? What are the strongly connected components? When done, so after the second call, the vertices in each tree that's a DFS tree from the second call. Are the strongly connected components of G. Okay, so there's a proof of this last bulleted item. It's a theorem in the textbook. I'm not going to prove it, obviously, but I am going to illustrate it. So we're going to do this And this is exactly what you are doing in PA3. All right. Maybe I'll just leave that there for a second. Okay, so here's our example. 1, 2, 3, 4, 5, 6, 7, 8. So notice we have some parallel edges. We have the edge 3 to 4 and the edge 4 to 3. That's possible in digraphs, not in undirected graphs. We have 6 to 7 and 7 to 6, two different directed edges. 3 to 7, 7 to 8, 4 to 8, and 8 to 8. Okay, so there's our digraph. Now let us run DFS and build the stack as we go. So here's our stack. And I'll draw the forest as we go. So discover 1. So the first call, we use our convention. Order the main loop by increasing vertex labels. 1, 2, 3, 4, 5, 6, 7, 8. There seems to be some question about this on Piazza, by the way. When the first call, the first run of DFS should just be in our ordinary order. 1, 2, 3, 4, 5, 6, 7, 8. That's the main loop. The second call where we change the order. So 1 is a root. Then 2 is discovered. That's a child. Then 3 is discovered as a child of 2. From 3, I can discover 4. And from 4, we can discover 8. From 8, we can discover nothing, so we finish 8, push it onto the stack. Return to 4. From 4, I can discover nothing, so I finish 4 and push it onto the stack. Return to 3. From 3, discover 7. I meant to have another branch here. So from 3, I discover 7. And from 7, I can discover 6. So 6 is a child of 7. From 6, you can discover nothing, so you finish 6 and push it onto the stack. Now return to 7, from which you can discover nothing, so finish it and push 7 onto the stack. From 7, return to 3. From 3, you can discover nothing, so you finish 3 and you push it onto the stack. And now return to 2. From 2, can't discover 6 anymore, but now you can discover 5 from 2. From 5, nothing new can be discovered, so you finish 5, push it onto the stack. Return to 2, nothing can be discovered, so finish 2. and push it onto the stack, and then finally return to 1. And from 1, you finish 1 and push it onto the stack. So there's your stack. That's the first step. And here's our DFS for us. Didn't actually need that. So this is G. What's G transpose? G transpose is a graph on the same set of vertices. This digraph has all the directions reversed. Okay, so don't let me make a mistake here, because if I make a mistake, it's going to mess everything up. Notice when you reverse a loop, it's the same thing. 8 to 8 is reversed is 8 to 8. Remember, you can always run these operations on the table, right? So you first fill in the adjacency list representation, and you can work your way through it that way, looking at the pseudocode. I would say, though, if you need to look at the pseudocode, which, on a test or a quiz you would have available, you need to look at the pseudocode, you don't know it well enough. Okay. This goes up, this would go up. Is that everything? That's everything. Okay, so now we have to run DFS again, except the main loop of DFS is run in stack order instead of increasing vertex label order. So here's the DFS forest. It's going to look different than this. As a matter of fact, it's going to have more than one tree in it. Okay, so here is, you just got to keep this stack in view. Well, we first execute visit 1. So visit 1. From 1, I'm in visit 1 now, so I go to the loop in visit 1. And that loop is still executed in our conventional order, increasing vertex label, the for loop in visit. So then you discover 5. Five is a child of 1. From 5, you discover 2. That's all you can discover. From 2, you can discover nothing. So you finish 2. Turns out the stack will be useful over here too, but I'll keep track of the stack here too. Even though, the second run of DFS has new finish times, the stack is going to be different. I'm using this stack to run the main loop of DFS, and I'm building a new stack as I go. Okay, so what did I just do? I finished 2. Then back to 5. So from 5, I can discover nothing new. So finish 5, push. From 5, I go back to 1, finish 1. Push that onto the stack. Now I'm back in the main loop of DFS. Right? I just finished 1, and that's where I started. Where do I go next? If I was using the normal convention, I would go to skip 2 and go to 3. But I should go to, well, it turns out I end up there anyway. But the next thing in the main loop of DFS is 2, but 2 has been discovered, so skip it. 5 has been discovered, so skip it. the next thing is 3. So 3 is discovered next in this order. So here's 3. We just popped the 3 off the stack. From 3, what can I discover? Well, 2's been discovered, 4 has not. From 4, we can discover nothing new, so we finish 4, push, return to 3, can discover nothing new, so finish 3, push. So now continue on the in the main loop of DFS by popping the next thing off of this stack. Is everybody seeing this? Yeah. Pop the 7 off. So 7 is the next thing we discover, and it's the next root. From 7, I can discover only 6. From 6, I can discover nothing, so I finish it, push. Return from 6 to 7. From 7, I can now discover nothing. So finish it, push. And then what's next? I'm back in the main loop of DFS. I have just popped the 7, did a whole, discovered the 7 and the 6. So I continue on the main loop of DFS in this order. But by now 6 has been discovered, so I skip it. 4 was discovered a while ago, so I skip it. The next thing is 8. So 8 is discovered, and there's nothing new to be discovered, so we finish 8. It has no children, and there's 8 in the stack. Okay, the theorem says that these vertex sets are the strongly connected components in our original diagraph. 152 is this group right here. Uh, 3, 4 is this group right here. 6, 7 is this group right here. And 8, the singleton, is this guy right here. So if you stare at that for a while, you'll see that these subsets are strongly connected. For instance, this is a directed cycle. This is a directed cycle. This is a directed cycle. And you can certainly get from 8 to 8. So each of these dotted sets are strongly connected. And once you get out of one of these dotted sets, you can't get back into it. So for instance, I could leave G by 3 routes. This edge, I could leave the group 1, 2, 5 by that edge, or that edge, but no edge leads into it. So that makes this a strongly connected component. Likewise, this is a strong component because you can't, once you get out, you can't get back in. So if you add a vertex to this group, you would lose strong connectivity. So these are in fact the strong components. Convince yourself of that. By the way, notice that the strongly connected components of G and the strongly connected components of G transpose are one and the same. They have to be, right? Because if X is reachable from Y and Y is reachable from X in this graph, then Y is reachable from X and X is reachable from Y in this graph. It's because of the very definition of transpose. All directed paths have been reversed. So the mutual reachability relation on vertices has been preserved. So these are also the strong components of G transpose. Not that anybody asked for those, but we've also found those. Okay, so all of this pertains, I hope you can see, to PH3, except for one thing. I've asked you to print out the strong components in topological sorted order. Well, topological sort of what? Topological sort of of the following graph, the component graph, also called the condensation graph. Of G, denoted GSCC, the graph of strongly connected components. So each strongly connected component of G is a vertex of GSCC. And so that's why it's called the condensation graph. It's as if all of these vertices in one component condense and coalesce into a single new vertex in the condensation graph. So we have 1, 2, 3, 4 vertices in the condensation graph, or graph of strongly connected components. And what are the edges? GSCC well, let's put it this way. The ordered pair, yeah, let's say they are C1, C2. These are the components. These are subsets of the vertex set. Call them C's. So CI, CJ is an edge in GSCC if and only if there exists X in CI, Y in CJ, such that XY is in the edge set of the original graph G. In other words, these two edges from 2 to 6 and 5 to 6 coalesce into a single edge from this component to this component in the condensation graph. This edge gives rise to an edge in the condensation graph from this component to this component, etc. So in our example, going back to the original graph, GSCC looks like this. I've got 1, 2, 5. That's a component. 3, 4. That's a component and therefore a vertex. 6, 7. That's a component. And 8. That's the component. And what edges we have? These two edges give rise to one edge. This edge gives rise to this edge. This edge from 3, 4 to the group 7, 6 gives us an edge here. And then the group 3, 4 to 8. And then the group 6, 7 to 8. Now take a look at GSCC. That's a digraph. Notice it is acyclic. It has to be acyclic. Because if it was possible, if there was a cycle of edges here, say an edge from here to here, here to here, and here to here, then it would be possible to go from this group to this group to this group to this group, back in the original graph, from here to here to here to here, the original graph. But that would mean that I could enlarge this supposedly maximal strongly connected component into a bigger subset, which was also strongly connected. Since this is maximal, that tells you such a circuit cannot exist in the original graph, and so therefore no cycle can exist in this graph. All right, so since it's acyclic, it has a topological sort. And what is the topological sort? Well, this Z, actually we've seen this graph before. This Z here tells you it has to be, there's only one of them, 1, 2, 5. I know I'm over, but just let me just finish my sentence and we'll quit. 3, 4, 6, 7, 8. Here's my Z. What else do I have? 1, 2, 5 to 6, 7. And I have another edge from 3, 4 to 8. So you can see that that is a topological sort. All right, so you're supposed to print these out in topological sorted order. And the key to doing that is the second stack, the stack after the second column. If you just read this, the stack from bottom to top, you'll see that it's already arranged in topological sorted order. So you have to print out this, then this, then this, then this. But how do you know the boundaries, right? What defines the boundary between strongly connected components in this stack? The parents is what gives it away. 8 has nil parent, 7 has nil parent, 3 has nil parent, and 1 has nil parent, because those are the roots. Now think of the nils as being like commas that separate within this stack, as you're reading from bottom to top, the strongly connected components. 2, 5, 1, reach a nil, go to the next line. 4, 3, reach a nil. 6, 7, reach a nil, go to the next line. 8. So that's how you're going to automatically get the topological sort. Notice, right? This group, then this group, then this group, then this group. It's right here. Okay, now I've gone a full 7 minutes over. I do apologize to that for that, and I want to just say sorry. I hope you forgive me, but I wanted to give you as much to go on when it comes to PA3 as possible. This is what you're doing in PA3. I will hang around for a few minutes because I imagine there are some more questions on PA3. And Vincent, you can take off if you want. I'm just going to allow people to unmute themselves now. Thanks for intervening on me when I needed to be intervened with. Mark Gonzalez, go ahead and unmute yourself. I'm pretty sure you have ability to do so now.
Yeah.
No. Yeah, you can. Okay, go ahead.
So I have a question. Basically, if between 6 and 7, there wasn't a one-way street back to 6 or back to 7, or even if there wasn't a link from 8 to 8, those components wouldn't necessarily be strongly connected. But
wait a second. The role that this loop plays is nothing. If that loop was not there, 8 would still be a strong component.
What about if you removed one of the links from 3 to 4 or 6 to 7? It would still be.
If I removed one of these links or one of these links, then these would not be strong components. I wouldn't have the group 6, 7. I think both 6 and 7. So you're asking me a hypothetical. Suppose I remove that edge, say, from 7 to 6. That would mean I can get from 6 to 7, but I don't see a way to get back from 7 to 6. No, there isn't. So these would have to be in separate
strongly connected components, and I'm pretty sure these singletons would then be strongly connected components on their own.
But
So yes.
my question is, when you run the DFS on GT at that point, there will still be a tree forest from 7 to 6, even if there isn't another link between 6 and 7, right?
All I can say is run the whole algorithm, create this stack. You're just assuming that the stack is going to look the same.
Mm.
You know, that nothing else is going to be different except the fact that I'm still going to have that tree because I still have 7 to 6, but not 6 to 7. Yeah, but are you sure 6 and 7 would be in the same order that they are now?
I'm not.
Yeah. So I absolutely encourage people to run experiments like that on many, many examples, just so that you can get to the bottom of all of these things. Do that experiment. Actually do it. As soon as we go offline here, just do it. And you'll see that the algorithm still works. You're going to have different strong components. And by the time you're done, there will be an extra tree here. 6 and 7 will be separate trees.
Okay, thank you, Professor.
Yeah, sure. So let me, who's next? Kittis, go ahead. Unmute yourself. Kittis, Michael?
Okay, yeah.
Okay, go ahead.
Okay, so this is for quiz 3, are we essentially, is quiz 3 going, not quiz 3, quiz 2 going to be different from the quiz 1, in which case that we're just dealing with code, here we're dealing with graphs?
Yeah, in quiz 2, I think I said at the beginning, quiz 2 pertains to BFS. The 2 problems, they both pertain to BFS, and so therefore they both pertain to graphs. But of course, who says they can't have code in them?
Okay, just wanted to know.
Yeah, they could have code. Okay, so Daniel Zuniga, go ahead.
Hi, Professor. I just had a quick question, just to get ahead, I guess, in the class. What's the next topic we're going to be looking at after?
Next topic after this. Okay, so, yeah. It's gonna have to be on Thursday, isn't it? Well, to tell you the truth, I have not made up my mind on it. It could be. I went over and looked at my notes on my shelf over here. Not sure exactly, but it could be heaps and priority queues, which I believe is chapter 6. It could be single source shortest paths in a weighted graph, which I believe is chapter 24. Or it could be binary search trees, which I believe is chapter 12. Maybe it's chapter 13, I don't know, 12 or 13. Okay. So it's going to be one of those.
That's
I'm
fine.
sorry, I haven't really made, I'm always kind of on the fence. I don't know what the right order to do things in, and I know I got to do these things. There might be something else. I might decide to go into hash tables. And there's a chapter on hash tables, and I don't remember exactly what chapter it's in. But I didn't used to run, you do this in 101. I used to do it in the old 12B, so I'm not exactly sure if I'm really going to do that or not. Sorry, I can't be more specific. So I don't actually know what I'm going to do Thursday.
Oh, okay. I mean, that's fine. Just so I can just get prepared in at least a little bit in advance, just skim the book or something.
Yeah. At least gives you 3 places to look.
Got it. All right. Thanks, Professor. Have a good one.
Yeah. Okay. I see no more hands. No more hands up. So I take it that we're good enough on PA3. I'll answer some more questions on PA3 on Thursday. Remember, I've extended it one day to Saturday, so you got a little breathing room in PA3. Don't forget the quiz tonight that does pertain to breadth first search, and I'll see you Thursday. Okay, guys, take it easy. Bye-bye.